Okay, good afternoon, everybody. Thanks for coming. My name is Patrick Altaie. I really expected to be there about 4 people that turned up after lunch and that keynote, so I appreciate you all coming. So yeah, today we're going to be talking about clustering and distributed data. Effectively, you've heard a lot of things about clustering. You've heard a lot about distributed data if you went to Manuel's talk, and a few others have talked about these things. This is going to be hopefully a little bit of fun. We're going to talk about the practical aspects. We're going to go through a little demo. It's going to be very exciting. We're going to have a great day, hopefully. So let's get to it. First of all, about myself. My name is Patrick. Obviously, we talked about that. I'm from Australia. Originally, I moved to the UK about 5 years ago, which is why I talk a bit funny. People sometimes tell me I sound Canadian, but speaking to the Canadians here, they all think I sound decidedly not Canadian. So I don't know what I do sound like. So let me know afterwards who I sound like. I work for a company called Icon Solutions. It's a small consultancy / product company based in Wimbledon in the UK. We do consultancy for financial services, and we also have an instant payments product called IPF, which is the Instant Payments Framework. There's also a shameless plug at the end, so look forward to that. So we're based in Wimbledon, so that means Wimbledon's famous for 2 things, the tennis and Icon Solutions. I'm not aware of anything else that Wimbledon's famous for, so feel free to ask me any questions about Wimbledon, I guess. I have been to the tennis. Disclaimer, there isn't one, okay? So we'll just move right on. I just thought it was cool everybody had a disclaimer, so I felt I needed one as well. Okay, let's see what we're going to talk about first in 45 minutes. It's going to be very exciting. First, we're going to talk about the concept of Akka clustering. People, like I said, a few people have run through it now, but hopefully I can give you a different perspective, different point of view on it. So we'll see how well I do. We'll talk about a cluster singleton and the problems that solves, and we're going to talk about state in an Akka cluster. So obviously, if you have multiple actors deployed in a cluster, how do you share the state and how do you deal with that? We're going to talk about Akka Distributed Data and CRDTs and what those things are and what that acronym actually stands for. I'm looking forward to that as well. And we're going to have a very ambitious demo, which will obviously work because this is a demo and demos always work. So let's see how that goes. So first of all, let's talk about Akka clustering. Akka clustering is a logical grouping of 1 to n actor systems. I say 1 because theoretically, I suppose you could have an Akka cluster of 1. It's kind of useless, but you can if you want. It's kind of like one of those, if a tree falls in the woods, if an Akka cluster starts by itself, did it even start? I don't know. So we can look into that. So yeah, you can have multiple actor systems running in a cluster. It lets you create a fault-tolerant application. So effectively, if one node, if one node on one data center is unavailable, then what happens then? You can have another node that's already started and it's picking up the load. So it may run a degraded service because it's having to deal with, for example, a bottleneck situation. But your application continues to run. It's like that visualization that Fabio had with the Terminator. I think that's a perfect example. So you'd be crawling on your hands, but you're crawling, and that's the important thing. It's decentralized, so there's not it's not a hub and spoke architecture. So there's not like one big boss central server. There is the concept of a leader, but there's no kind of central authority that decides, kind of like MongoDB, I suppose, with a primary. There's not really, I suppose there is a leader, but it's a bit different. It's more distributed than MongoDB, I guess, for those of you who are familiar with that. It's gossip-based, so it's a Cartesian product of all nodes having to have availability of all, reachability of all other nodes. So one node A has to be able to talk to node B, C, and D in a kind of a 4-node cluster, and B has to be able to talk to A, C, and D, and so on. So everybody has to be able to reach everybody else. There's some other interesting things. So ACT systems in a cluster can be heterogeneous, so they don't need to all look exactly the same. So you don't need to have, for example, in a 4-node cluster, you don't have to have 4 nodes that look exactly the same as each other. You can have different ACT systems that, as long as they know how to talk to each other via mailboxes, or tell and ask and things like that, maybe they use the same domain, they don't actually need to look exactly the same. So you might have your application split in half. You have one actor, but then it's actually running a cluster.
So they don't all have to be, I guess what I'm trying to say, cookie cutters of each other. They also have, well, Akka gives you the capability of, well, it actually handles the availability and reachability of all the nodes. So if you attended Manuel's talk, he was talking about the fire crawl detector, which gives you essentially a measure of trustability that something has gone wrong with a specific node. So that's quite interesting. So that's done for you, which is really good. So you don't have to write any custom code for managing that kind of situation. Joining and leaving is all managed by Akka. Obviously, you have to deal with those situations. You can even choose to listen to those cluster events if you want to do something special when a node joins or when a node leaves. And it supports, obviously, CRDTs. So we'll talk about what that is in a second. So now that's great. You've got an Akka cluster running. You've got multiple Akka systems running in a cluster. One of them is running in Europe. One of them is running in the US. One of them is running in China or whatever. And look, it's all great. This is fantastic. This is what distributed computing is all about. Wait. Hang on. Wait. We have a problem. So what if I have global state, for example, in my application, but now I've got 4 Akka systems. If they're cookie cutter, if they're all clones of each other, now they've got their own state, but now they're all maintaining their own individual state, not globally, but they're in a cluster, but they've got their own state, but they're in a cluster. So we have a bit of a situation there. For example, if I have multiple nodes running on the same machine, if I need to bind to a port or similarly need access to some resource, that's an interesting challenge as well. So if there's multiple of us, but only one of us is allowed to access a specific resource. A good example, aside from a port in a distributed system is, for example, legacy applications. I've seen situations at Icon where I work where you've got legacy systems. They say, oh, this thing runs over IBM MQ, for example, but you can only have one consumer. Why? Oh, because it's a mainframe application and only talks using tab-separated values or whatever. I mean, it's some legacy thing. We've all been there. So how do you manage that? And you also, what if you need to coordinate actions in a cluster system? So a good example of this is a scheduler. So say you have a scheduler that runs every 30 seconds or something that runs against a DB that says, find me all transactions that haven't completed in what have I dropped on the floor effectively? If I've dropped any transactions, has there been any incomplete issues, any incomplete transactions, things like that? I don't want to be having multiple queries be running at the same time against the DB. That's not good, and then just things will start happening repeatedly, which I only want to happen once. So to that end, what we can do is we can use the concept of a cluster singleton. A cluster singleton effectively runs on the oldest node in the cluster, also sometimes known as a leader, and it's very straightforward. Again, if you attended Manuel's talk, there's no question about who the leader is because it's sorted in a deterministic way. The list of members. So the first one in the list is usually the oldest one, and that's where the cluster singleton runs. In our demonstration, we're going to talk about that. We're going to see what that looks like, and we're going to see how to create one as well. So what else can you do? Any actor can be created as a cluster singleton. You don't have to have a scheduler. You don't have to be accessing MQ because somebody's sending you tab-separated values. It doesn't have to be a specific special actor. It can be any actor can be created as a cluster singleton. And Akka, and this is the power of this, Akka ensures that only one instance of that cluster singleton runs across in a cluster. So you don't have to worry about situations where, but what if there's a second one? Oh, but then they've just left and so on. So it's all dealt with, which is really good. And we're seeing some great great time savings and not having to worry about these things where we're seeing at clients anyway. So that's been really helpful for us to effectively say, okay, Akka does all this for us. We don't need to worry, and it's all good. So that works really well. Wait, there's another problem. Hang on. So now I've got all these different nodes. Okay, so that's great. So we solved the cluster singleton problem. It's all great. But now we have a new issue, which is now there's state that's available in node 1, but node 2 doesn't know about that state. So what if, for example, I have Kafka is a big thing. We've heard a lot about Kafka today. What if I have data in node 2 that received a message over Kafka, but then that information needs to be available to all the other nodes, for example, something along those lines. They're in 2 different consumer groups. Now you have a situation where only this node knows about it. And what if there's a conflict? What if we have like a topic subscriber or something like that, and then multiple nodes are receiving the same message? It can happen. Or sometimes you want that to happen. So how do you deal with that situation? So these are all interesting questions, which thankfully solvable by Akka Distributed Data, which is the second concept that I'd like to introduce aside from clustering. Distributed data is a fancy, I don't know why I called it fancy, I guess it is fancy. It's an eventually consistent distributed store. One of the reactive kind of manifesto concepts is eventual consistency. So I need to have multiple, if I have multiple nodes in an active system, in an active system cluster, they all need to be able to share the same information without any conflicts. You decide the consistency requirement. What that means is you have a situation where, okay, I've received 2 bits, sorry, I'd like to save some information into the distributed data store. You can decide when Akka will report back to you when that's done. So you've got a few options. One of them is write local. And what that means is write it to my local store, and I'll rely on the distributed data gossip to actually propagate that information across to other nodes. You can do write majority, which says effectively write it to n divided by 2 plus 1 nodes, so one more than half the number of nodes available in my cluster, and then get back to me. Or you can say write all, which says don't come back until everybody has learned about this information. So those are the 3 options. So you control the write consistency, which effectively says, only give me a callback. So it's an ask pattern effectively. Only give me a callback when something, at a specific point in time that I decide, which I think is pretty powerful, and it depends on your use case, I suppose. So if you want guarantees, then you can do a write all, but it might take a bit longer. If you don't really care and you don't really mind if something happens before the data is written, then you can say, do you know what? That's fine. Just write local, and then I'm not fussed. The way you do all of this stuff is very straightforward. Akka supplies you a replicator actor, and I'm sure half of you are about to leave this room. This is in Java, not Scala, so I'm sorry in advance. But there's a replicator actor you get. This is the Java example, very similar in Java and Scala as well. And so effectively, this supplies you an actor ref, and then you send the actor ref some tiny types like update or get, and then it calls you back whether update success or update failure or get success or get failure. So we'll look into those examples as well. Now, how do you solve the conflict problem? Because if we scroll back just one slide, what if we have a conflict? This is one of the issues that we had in an active system in a cluster. What if we have a conflict? The way we can solve a conflict problem, all values, or all the, not really values, it's actually all the types that you store in this distributed data store has to be a conflict-free replicated data type, or a CRDT. And what that means is, effectively, you have to implement a merge function. So Akka might come to you and say, hey, I've got 2 different nodes that have reported the same information. How do you want to deal with this? So it's not really conflict-free. It's more like, you deal with the conflict, and it offloads the conflict resolution up to you, and there's obviously some pre-rolled ones or supplied ones that come with Akka. So there's some very exciting acronyms here that we all have to get familiar with. We get to know our CRDT lingo here. Oh, that works. Okay, that's good. We can all get familiar with CRDT lingo here. So a G counter means you can grow. So that means it's a counter that only goes up in one direction, which is very straightforward. PN is a positive negative counter. So it can go up and down, but with an asterisk, a PN counter is actually 2 G counters, one of them that goes up and one of them that goes down. Sorry, that's PN. OR, observe, remove. This is a concept where effectively, if you've both made the same write, one of you removes, if you've observed the same write, then you can remove your one, and then you eventually have a consistent view of the data. Won't go into too much detail into that. And then LWW is my favorite one because it's the easiest one to explain. It's actually all in the name. Last writer wins. So effectively, every time you write something, it goes into the DB and it says, hey, I wrote this value at X time, and you wrote this value at Y time. You wrote it last, you win, I'm going to delete my value. So it's pretty straightforward. The values that you're seeing at the bottom, these types that you're seeing at the bottom here, I don't know if you can see that. Anyway, oh yeah, you can, there you go. So these values that you're seeing at the bottom here are the ones supplied by the Akka framework, but you can implement your own data type. you can roll your own effectively, and it has to implement, I think, an interface called distributed data or something along those lines, and that means you must implement a merge function. So you can decide how to merge things, which is very exciting if you want to do that sort of thing. But these tend to work out quite well. I should have probably explained what the things are. So a set and a map are pretty straightforward. I think we're all familiar with what a set and a map is. A register is just a thing, so you can just store a thing in distributed data, so any object, effectively. A flag is a flag. Okay, maybe I didn't need to explain these things. There you go, it's very straightforward. So yeah, counters, maps, sets, registers, and flags. And that's the lingo. So let's talk about an example. And this is kind of a ridiculous example. I know today we've been talking about Lagom and all these other really advanced things, and here I am telling you about TFTP, so it's a bit ridiculous. We've rewound to like 1992, so bear with me at 3 o'clock in the afternoon. So, okay, so I'll tell you a bit of a story about why I decided to do this and why this whole thing is happening to you effectively. Essentially, in one of my client visits, I was at a client site, and with a client experience, if some of you have worked with consultancies, you know, they give you practically the worst seat in the worst building, in the worst corner of the office, where you're getting blasted by air conditioning and all this other stuff. You know, I see some heads nodding, so you know what I'm talking about. So yeah, you know, so I'm in this dark, cold, damp corner in the office. This is the UK as well, so it's always freezing and it's always raining. So I hope I'm painting the right picture here. And so anyway, so they gave me this desk for a week or whatever, and I was sitting there. And and the other thing is, there's never any network connectivity because you're in the corner. Like the Wi-Fi never reaches. Network cables, like the little pin thingy, has like been been flicked off and all this other stuff. So the cable's always coming out. Yeah. Anyway, it's fine. This isn't like a therapy session or anything, so it's fine. This is okay. So one of the other features of this desk that I was sitting at was an IP phone, which didn't work, obviously. But the IP phone had this really ridiculous thing that it did, which every 5 seconds it would come up and it would say, "No TFTP connection," which I wouldn't notice otherwise, except it flashed a red light every 5 seconds every time it did this for like an 8-hour day. I don't know how many 5-second periods are there in an 8-hour day, but I assume it's a lot. So that it got very annoying, got on my nerves, and so I thought, oh, actually, TFTP is a good example that we can prove reliability, or resiliency with anyway, with Akka. And it's actually, I would say, in like 1992, who knew that TFTP is like the championing push-pull stream processing? So it's the original fast data application. So you got to look out for that one, okay? Which is a proof that this stuff has been around for much longer than we think. Okay, so let's talk about what it is. It's a subset of FTP. We'll talk about why that's the case and why it exists. It's usually for network hardware to get its initial configuration, usually. So because you've got 0 configuration at the beginning, and then you kind of go to a default host or something along those lines and download your configuration. It's really popular with like PoE, Power over Ethernet devices like VoIP phones or switches or routers and things like that. And then you can connect to them with SSH or something along those lines once they've got their configuration. So it's super rudimentary, very easy to implement, and that's why it's trivial. There's the RFC. I don't know why I've made it URL as if you can click it, but whatever. You can click it, just click it in your minds. It's a lockstep protocol. I'll explain what that means in a second. And there's 5 message types. The requirements that I just invented, it has to be resilient. So if one node of my TFTP server goes down, then another node should be able to handle it. And it's distributed, so I can deploy my TFTP application for being really fancy behind some load balancer or something like that, but we're not going to get that fancy, unfortunately. Cue mass walkout. No, but okay, so let's talk about the 5 different message types. So the message types, very straightforward. Effectively, this is highly scientific. I hope you're paying attention. So the first one is, everything has an opcode, which is like a 2-byte a 2-byte space in the UDP. Oh, it's UDP based, by the way, which is very exciting. So it's 2 bytes in the UDP packet that says, the first 2 bytes say which opcode it is, which is what type of message this is, okay? It's like a really rudimentary schema, okay? Again, this is 1992, so we didn't have schemas back then. Well, I guess we did, but anyway. So yeah, the opcode says, opcode number 1 says read request. So this is like a TFTP get, an FTP get actually. It doesn't really matter, it's the same thing. So it goes from the client to the server. The client connects to the server and it says, hey, I'd like this file.
And there's also a point about a transfer mode, which is ASCII or octet. So you can get it as ASCII text, or you can get it as bytes. It doesn't really matter, not relevant for this case. The second thing, a write request. So a write request being a TFTP or an FTP put. So you can put a specific file at a specific location. So it's bidirectional. That's a good thing about TFTP as well. And that goes from the client to the server again. And here's where the lockstep bit comes in. So the TFTP protocol, after a read, oh, by the way, the write request we don't implement in this particular application, but it's on GitHub, so you can issue a pull request if you want to learn about TFTP. I don't know why you do that to yourself, but whatever. So the opcode 3 is a data block. So what happens is when the server receives a write request, a read request, sorry, it says, hey, I'd like this file from the server. And what happens is, because it's a lockstep protocol, what that means is the server just sits there waiting for messages, and then it receives a read request, which causes a trigger, which triggers it to actually send the first data block. Okay, so a data block is effectively a 0 to 512 byte block of data, which has a number, a sequential number. So I receive a read request, I send back a data block whose number is 1. So I say, okay, this is the first 512 bytes, or if the file is smaller than 512 bytes, it's whatever, however many bytes there are. And then what happens is the client receiving that data block triggers them to send me an ACK saying, okay, I've received that, now send me the next one. Me receiving that ACK triggers me to send the data block back saying, okay, here's block number 2. Them receiving block number 2 triggers them to send an ACK back to me saying, okay, I've received block 2. Then that triggers me to send block 3. Then they say, okay, I've got block 3. Okay, now block 4. So it's lockstep because effectively the receipt of one message triggers the send of another message. There's no session, there's no socket, there's no kind of like a WebSocket push or anything like that. Effectively, you just receive a packet, it triggers you to send something else. And that's what they mean by a lockstep protocol. So a typical exchange in our really modern application is one read request, and then lots of data blocks and ACK, data block, ACK, data block, ACK. So the server, I send a data block, I receive an ACK, which triggers me to send a data block, which triggers them to send an ACK, which triggers me to send a data block, and then so on for the rest of our lives. Well, not really, until the end of the file, so until we reach the end of the file. And then finally, which is a situation you never want to be in, which is when bad things happen, which is the error, okay? And either side can send this. For example, if you're trying to receive a file, and it fails, for example, you run out of space, you can send an error block saying, wait, stop sending the file because I have no idea what I'm doing anymore. I've run out of space, no space left on device. We've all seen that error message, I think, on Unix anyway. I don't know what's happened to the emoji there as well, but whatever. Such is life, you know. Okay, so that's the TFTP message application. Pretty straightforward, I think. It's not exactly rocket science. So let's move on to the next bit, which is the architecture. I mean, I really use architecture in inverted commas. I wouldn't say this is architecture, but whatever. So this is what a single node looks like, okay? So you have a server. We should probably introduce the key first. You have a thing, anything blue is a cluster singleton. So the server is a cluster singleton because I have 2 nodes running on the same machine. I can't have two instances of the server running at once because I'm going to get a bind exception. That's right. So what's going to happen? I can't do that, so I'm going to make it a cluster singleton. You can tell this is a really contrived example. I have anything with a solid outline that's orange is a user actor, so it's kind of a long-lived actor. And we have the concept that we use at Icon called an ephemeral actor. It's kind of like an ask pattern, which is an actor that we start up on demand, and then it shuts itself down after it completes its task. And finally, we have the magical replicator actor, which is provided to you by Akka. So what happens is, effectively, I listen to UDP port 13337 UDP, and then what happens is they connect to me. So I have a client that connects to me with a client socket. What happens is they send me a TFTP message and it says, hey, can you get me this file? Or I want you to write this file, or there's been an error. So this server effectively has a really rudimentary router which effectively says, oh, this is a read message, a read request? Okay, send it to the read request actor. Oh, this is a write request? Send it to the write request actor. This is an error? Send it to the error actor. This is an ACK? Oh, this is a lockstep protocol. So what I have to do is an ACK makes me trigger sending of the next segment. So what I say is, I say, well, let's talk about a read request. Let's talk about like a traditional, like a typical flow, effectively. So somebody connects to me and they say, hey, can you please give me this file? So what happens is the opcode is 1, I go to the read request actor, and then the read request actor says, okay, they want this file. There's an issue already. Can you believe it? So the problem is the file that they request is only present in the initial read request. Okay? So my server dies. Now I don't know what file they wanted. They might send me an ACK saying, hey, this is, oh, I'd like block 4. And you say, what the hell are you talking about? I don't know. Of what? Block 4 of what? I have lots of files on this server. Which file do you want? So we have to store that somehow. We have to store what request it is that they want. So you can already see in your minds a map forming here of client and file, which is which client and what file do they want. Because every time they send me an ACK, they're sending it to me from the same client socket. So they're saying, oh, please give me the next file. I say, okay, I don't know what file you want, but I know who you are. So I can look in my distributed data map, and I can say, look, okay, I see. You didn't tell me what file you want, but I'm not upset. That's fine. You want this file, that's okay, because I've saved it. So my read request actor, the first thing it does is it saves the consumer to the replicator. Well, it asks the replicator to save the consumer. It says, hey, I've got a new request. Can you save it to the distributed data cache, distributed data map, sorry, such that if I die, then somebody else is able to handle the request. So then what that does is, actually it's not shown here, but effectively the read request actor triggers the segment sender to send segment number 1. So it says it's a lockstep protocol, so I must send segment number 1. And then what happens is I need to say, okay, segment number 1 sent, I must wait until they send me the ACK. Okay, they've sent me the ACK. So what happens is I receive the ACK. Then what I can do is, because I received the ACK, I'm running in the cluster, so I might not know who this is. So what I have to do is, when I receive the ACK, I ask the distributed data store again. I say, which file did they want again? And then what that says, oh, they want this file. Okay, so then we send the next segment. And that's how it goes, effectively. I send the ACK, the segment sender, the previous ACK, I increment by 1, and I say, please send them the next segment. If there are no more segments, and this is the really super advanced way you indicate the termination of a transfer, you send them a 0-byte packet. So effectively you say, oh, this is a data packet, but it's empty. And that's how you signal the end of a transfer, which is, so you can see why it's called trivial file transfer protocol, because it's extremely trivial. So yeah, so that's really it. And oh yeah, obviously the segment sender sends the data blocks to a consumer. And okay, so let's see what else. I think that's quite clear. Probably a little bit confusing, but we'll look at the code in a second. We'll look at the code right now. So let's have a look. Now this is where everything breaks down because I have to move to mirror mode. Oh, okay, here we go. Okay, great, fantastic. It worked. So. Okay, so let's go into presentation mode, which is like, you can never get out of presentation mode, but that's fine. We'll get into it. So I don't know how I'm going to do this. So let us look at demo time. No, let's not look at demo time. Let us look at the architecture. So the architecture says we have a server. Okay, so let's look at the server first. So initially I have, as like the entry point, I have a thing called the runner. And the runner loads a file called application.conf. So we're going to look into how you can actually make your configuration load an application, create your active system in a cluster. We'll look at that. In fact, should we look at that now? Yeah, let's look at that now. So application.conf, forget all of this stuff. It looks really exciting, but don't worry about it. All that you need to say is actor.provider equals cluster. Okay, you're running a cluster. Well done, congratulations. You're now running a cluster. Okay, you can be running a cluster of 1. This is that if a tree falls in the woods situation, but I don't really care, okay? This is actually the, and then you specify a concept of a seed node. A seed node is not like a MongoDB primary. It's not like a boss of the cluster or anything like that. It's just who am I able to reach out to get information about all the other nodes? Because obviously when you start, there's no multicast. For those of you who were in that conversation about multicast, I can't remember which one it was. But anyway, because there's no multicast, it's kind of just using regular TCP. I need to talk to somebody first to find out about the rest of them. If it was multicast, it would be a little bit simpler, but we won't go there. This is using a slightly older way of configuring. Now there's a thing called Akka Cluster Bootstrap, which actually lets you specify some bootstraps. So it was very, very, it's a lot nicer, but anyway, this is using a classic way of doing it. So you start your application in a cluster. Okay, I'm running on localhost 2551 in this case. Okay, so let's go into our runner application. We create an active system. It's not that exciting. Now, let's look at how we can create a cluster singleton, okay? So my cluster singleton, if we flip back to the presentation, says is the server. Okay, so the server actor has to be the cluster singleton. So let's create our server as a cluster singleton. Initially, we grab cluster singleton manager settings, which we pass as a parameter to cluster singleton manager props. Effectively, you just give it regular props in Java. I know this is not Scala, so thank you all for not running out of the room with your hair on fire. So effectively, it's just a regular props. You say, hey, create me a server, and this is like really rudimentary dependency injection where I'm saying, hey, create me a server, and then give me like a read request actor, a write request actor, an error actor, an ACK actor. These all look pretty straightforward, right? Because the server has references to read request, write request, ACK actor, and error actor. So it's like really, really crappy dependency injection just to make a point. You might see this thing here called poisonpill.getInstance. What is this? So if we look at the properties here, these properties? No, I'm telling you lies, not these properties. These properties. So the second parameter is termination message. So effectively what you can do is you can tell your actor, you probably know that you're a cluster singleton. I'm just letting you know you're probably a cluster singleton. Well, you will be a cluster singleton, you have no choice. So what you can do is you can, instead of just telling it a context.stop or a poison pill, what you can do is you can say, oh, by the way, you're in a special situation now where I'm asking you to stop being the cluster singleton specifically. So if you want any specific behavior to happen, specifically when you as a cluster member are stopped, cluster singleton are stopped, then you can do this specific behavior. So you can make it like a string, or you can do whatever you like. So that's an interesting thing. In this case, we're just saying, oh, if you want to stop the cluster singleton, just give it a poison pill. I don't really care. There's no special behavior. But that's an interesting thing to know when you start a cluster singleton, to say, oh, do you know what? You can actually give it special behavior to say, wait, you're not just being stopped. You're being stopped in a really nice way, which is you're being stopped as a cluster singleton. So look out for that. And the third one is cluster singleton manager settings, which we just pass straight through from the Akka system. We're going to call it server singleton. We're going to print out a nice message. We're just going to impress us all, okay? So let's look at our server. So again, let's look back at the architecture. So we've created a server, which is a cluster singleton, and we've created these 4 read request, write request, error, and ACK actors. So if we look at our server, some interesting things happen here. The server effectively runs on this host and then this port. You might remember if we flip back to the presentation, you can see that we run on 13337. This runs on 13337. Believe it or not, and this was impressive, I didn't realize this, you can actually ask Akka to bind to a UDP port. you can bind an actor system to a UDP port, which is pretty impressive. And then it just sends you UDP packets as tells, which is pretty amazing, I thought. So who knew? But anyway, it's available in the docs. I don't know why you'd ever want to do this, apart from build a TFTP server. But anyway, here you go. So effectively, we have, again, this rudimentary disaster of dependency injection continues. And so we effectively have a map that says, hey, based on the opcode, if it's a read request, send them a read request. Send that read request to the read request actor, send the write request to the write request actor, and so on. And then finally, we use this tiny type. As you know, Akka operates with all these tiny types like, bind or well, we'll look at all the others. So we ask the UDP manager to bind to that specific port, and then we wait for them to give me a bound message, which says, hey, okay, you've asked to bind to 13337, you've bound. So effectively what I can do is now, I can say, hey, the only way that this could actually happen is if I'm the cluster singleton, because I'm being started as a cluster singleton, Akka guarantees only one instance of this server is started as in the cluster, and so I can safely make the assumption that if I've received a bound message from the actor system, then I'm the cluster singleton, and I log it as such, just for posterity, and also for demonstration purposes. Then what I can do is I can also use the become, which some of you might be familiar with. So become and unbecome are kind of typical Akka behavior. So what I can do is I can say, hey, I'm now ready to receive actual messages, because before binding to the port, I can't say that I'm ready to receive messages. When I'm bound, okay, now I'm ready to receive TFTP messages, okay? Okay, I've received, and the way that you receive packets from TFTP, from Akka is you see udp.received, which is literally just a byte array, which is very exciting. And then I get the opcode and I say, okay, the opcode is 1, so I say get actormap.get by the opcode and tell them this particular byte array. Okay, so it's on the individual actors, like the read request actor, the write request actor, and the error actor to deal with that situation. They say, hey, I've got an array of bytes. It's kind of like a schema, effectively. So I've parsed the schema, and they say, oh, this schema version is read request. And so effectively, I send the read request to the read request actor, which only understands read requests.
And what else? Okay, so that's the server. So now let's look at the read request actor and how we can actually communicate with the distributed data store, which is what we're all here for. So without further ado, let us go to the read request actor. Now, there's some interesting thing here. So it receives a UDP receive, which is the byte array, okay? And I say, hey, handle received. There's some really exciting stuff happening with bytes and files and things like that. But anyway, the most important thing here is we store the requester, okay? The requester being the client socket, client UDP socket, blah, with read request blah in the CRDT store. And the way this actually works is this tiny type that I was telling you about. So you send a type called update to the replicator actor, and then you can see the replicator actor has been instantiated here. Oops, from this distributed data.get. I haven't done anything special, but I have to be running a cluster. And I tell the replicator, hey, can you update me with, I'd like to send an update saying, this is a last writer wins map because we're using this LWW map, and the map key is the INET circuit address of the client, and then the value is the read request. Well, it's actually the entire read request, which is what file do they want and what mode do they want it, which is it binary or is it text, but it's not really a big deal. So I create a new update and I say tell to the replicator. And then you can see here, the replicator calls me back and it says, oh, update success. And then I can say, okay, update success. It's not a big deal, I don't really care, because I'm the read request actor. And then in this case, I create a segment sender. And the segment sender, again, very exciting stuff with bytes, it doesn't really matter. But at the end of the day, after it's sent a block number whatever to whatever, as in block to INET socket address, it stops itself. And that's why it's got this kind of a dotted line around it, because the sole purpose of a segment sender is to, wait for it, send a segment. And so effectively what happens is I just say, start yourself very temporarily to just send this one block to that particular socket, and then stop yourself. You don't have to make it like that, but I thought, it was another interesting demonstration of that kind of thing. So now what we've done here is the read request actor saves the consumer to the replicator, okay? Now let's look at the ACK actor retrieving consumers. So if we look at the ACK actor says, hey, I've received an ACK, okay, but I'd like to read, using this read majority, so this is that concurrency, the consistency that I was telling you about. So you can say, I'd like to read the consistent view from everybody, or consistent view from half plus one of the nodes, or consistent view from just my local, of whatever that value is. And it says, it calls me back and it says, get success. Here's the map that you asked for. And then I can say, okay, get success, and then I can get the value. And I can, again, like as you can see here, another use for the segment sender to say, hey, send another segment to this customer and then stop yourself. So there's a lot of actors starting and stopping, but it's pretty cheap, so it's no big deal. So what we're going to do now is try to exit out of presentation mode. Okay, we've exited out of presentation mode, that's good. I thought that was going to take longer than usual, which is good. Okay, so I think that's pretty straightforward, right? So it's really not that complicated, because thankfully TFTP is not that complicated. The server's a class singleton. I have some messages that I need to handle, and then I have a map that's in the distributed store. Okay, so what we're going to do is we're now going to run a demo that will definitely work, featuring the trademark 2 terminals side by side. So, okay. So I have 3 shell scripts here, which is very exciting. I hope you're paying attention. This is a really very complicated script. So effectively, this just starts my application. Okay. Node 1. I'll explain what node 1, node 2, and node n are. So let's look at this thing. So it prints there, welcome to blah blah blah, welcome to Akka, which is the runner. And then look at this. After a while, it says I'm the cluster singleton. It bound to port 13337. Now, I made this script called make random, okay? Make random is, again, very advanced stuff, okay? I hope you're focusing. Make random effectively calls head on the first n number of megabytes, or any file size, of view random. So this randomly generated file is going to be like cryptographically secure because it's really important. Not really. And then it saves it to my home directory and $2. So we call it using make random.
the file size. So let's make a random size file of, let's say, 11 megabytes or something like that. I don't know why. And we'll save it to rs18. Okay, so that's gonna create a file, a random file called rs18, which is this big. Okay. And so what's going to happen is we're going to run a TFTP transfer. So we're going to go to downloads and pretend this is proper, okay? We're going to go TFTP localhost 1337, get home rs18. Now, this thing is going nuts. This is a single node, by the way. I mean, obviously this is going to work, right? This is very, who cares? It's really simple, okay? It's a single node, nobody cares. So what's happening is, as you can see, there's this, what am I trying to say? The lockstep protocol. So effectively, I send a block. So in this case, I sent block 22,527, and I received I received an ACK for it. I sent the next block. I received an ACK. I sent the next block, and I received an ACK. It's very straightforward. So now let's do something a little bit more advanced. Let's start node 2. Oh, by the way, node 2 is very straightforward. All it does is it just overrides the ports, because I don't listen on Akka remoting on the same port. It's not going to work otherwise. So if I start node 2, I don't have to stop them both or anything like that. So it says, hey, receiving gossip. So they've magically connected to each other because I've specified a seed node. Okay? And then this thing, look at this. You've got this thing called a cluster singleton manager, which says, oh, wait, I was going to try to start a cluster singleton, but I'm not going to because there's somebody else in the cluster who's a cluster singleton, so I'm not going to bother. And you can trust me on this. If I run a transfer, it's going to work. But what we are going to do is we're going to try something very exciting, which is we're going to transfer a file, murder the first node, and then we're going to watch the transfer keep going on the second node because everything's being stored in the distributed data store, and it's going to work. And it's going to be really amazing. Okay, so not that I'm not that I'm hyping it up or anything. So we're going to TFTP localhost 1337. This is going to take a bit of quick alt tabbing because this file gets transmitted really quickly. So what I'm going to do is I'm going to get my file. Okay. So we're going to see it going nuts on here, and then I'm going to Control C this one here, or kill -9 or whatever you want to do, and then it should resume on this node here. So this is obviously going to work, and it's going to be great, and let's give it a go. Okay, Control C here. Let's see what happens here. If we wait a little bit. Hey, look at that. It started working on the second node. Okay. And there you go. And this exact same file was transmitted. And the only way that this worked is because the TFTP client, when it doesn't receive the next data packet, what happens is it retries. It retries and says, OK, I received an ACK. I was sending an ACK. I got the file. I got this block. OK, no response. OK, I got this block, and then we started replying again from the second node because it came online. It says, oh, I'm the cluster singleton now because the other node is unavailable. And you saw that it was pretty seamless, I mean, in what happens. And obviously, this is a really kind of a simplistic example. You don't need to, you can kind of extrapolate it to more advanced examples. It doesn't have to be this rudimentary. So that was the very exciting demo. And the final thing that I want to talk to you about is some pitfalls, okay? So it's not all rosy. Obviously, the demo worked perfectly because demos always work, and this is really great. But not everything is always great. So Akka clustering. You may have heard, if you've been to presentations, today or yesterday, about split brain, which is when situations where you have two clusters running at once that both think that they're the only cluster that's running. Say, for example, you have two active systems that are running on, you have a cluster that's running across two DCs, for example, and then the link is severed between the two. So you say, oh, well, I can't access any on the second DC, but that's fine. I must be the only cluster here. But there's actually two clusters. So there's different ways you can resolve it. You can use an arbiter that's external, for example, MongoDB, which uses like a 2+1. So you can do that. If I'm in the majority, then I can continue. If I'm not in the majority, I can stop myself, and things like that to prevent a split brain. That's possible. There's an interesting point about Akka Distributed Data, which is here it was blazing fast because it's on localhost, but Akka Distributed Data is not blazing fast. For the write majority, we were talking about this consistency guarantee, which is do I write all, write local, write many. It slows down as there are more. It's kind of ON as more nodes join the cluster. There's more gossip that has to happen between them, and obviously all of this stuff is we'll talk about it next. If you do want blazing fast data, kind of fast but lossy, you can use a concept of Akka Distributed PubSub, which is kind of like a topic, it's got its own topic broker inside the Akka system. That's something you can do. Akka Distributed Data is not for big data. Don't put your Hadoop cluster in this thing. This is not going to work because you can only have 100,000 top-level elements. Everything is held in memory. You're going to have a bad time. So don't do that. And the replication gets slower and slower, obviously. If I have more things to push over the network, then we're going to have a situation, and I don't recommend that. So what else was I going to show you? I think that was it, really. Oops. Sorry. Yeah, so that's it, really. So there are some downfalls. But feel free to have a look. The presentation is on GitHub. You can have a look over there. But you can see you've been seeing my handle on there anyway, so it's no big deal. And as a final shameless plug, if you live on planet Earth, we're hiring Java devs, architects. It's in Wimbledon, so you get to watch some tennis sometimes. We also have IPF for instant payments, if you have some issues with instant payments, if you're working at banks and things like that. And I think that's it. Yeah, thank you very much. Alrighty, I think we have like 3.5 minutes for questions. So if you've got any questions, I think you have to come up to the mic or yell it at me and I can repeat it. Any questions?
You showed the cluster singleton.
Yeah.
Is there a similar type of thing for per node?
Oh, you mean like a single actor per node?
Well, I mean, if you're putting up a server that's binding to a port, right?
Yeah.
You could do that one per node.
Yeah, absolutely. Yeah, you could definitely do that. In that case, well, we have this situation actually in our application that we build this IPF application. What we do is by configuration, we change it. So, for example, you have multiple actors that need to bind on different ports, like for different. We have different APIs, for example, that bind on different ports. We just manage it by configuration. So we package our stuff with Docker, so you can say, okay, well, service 1 needs to listen on port 1, service 2 needs to listen on port 2, and so on. So yeah, that's how we manage it, usually by configuration instead of using any Akka features. That tends to work for us, but yeah, I'm sure it's possible to, that could work.
Okay, thanks.
Thanks. Any other questions? You can yell them at me, I can repeat as well. You don't have to walk up to the thing. Yeah, so the question is about 100,000 top-level elements. So 100,000 top-level elements is across the whole cluster. So you must only store up to 100,000. And by 100,000, by the way, I mean those LWW map and OR set, so all of those top-level elements. You can only have 100,000 of those across an entire cluster, not per node, because remember, this thing is replicated, but the kind of canonical information is the same. We're all sharing the same information, but it has to be, it's a single source, but it's distributed. It's kind of like Napster or P2P or whatever, So yeah, it's 100,000 at the entire cluster level. I definitely don't recommend using it for big data or anything. Definitely offload that onto like, big data storage or whatever. But it's helpful in situations like this. Similarly, I don't recommend you do it for storing large objects. You can do, like, for those of you who've worked in EIP days, like a claim check pattern. So you can just hold a reference to the file like I'm doing here instead of the entire file itself. You can say, oh, this customer wanted this file, this client wanted this file, and that can work. So you can have lightweight storage in there. I recommend that. And it's lossless, but it's slow. That's the other issue. Okay, thanks. One final question? Oh, we're out of time? Okay, we're out of time. Okay, thank you very much, everybody.